So, linear decompression based schemes, so they actually use some linear network for decompression purpose. So, from the ATE or from the from the ATE, so we get some coded pattern, and that coded pattern passes through a decompressor circuitry to decompress into the test pattern that will be fed to different scan chains. Like in this case, so maybe from the ATE, so we are getting 4-bit into a code, and that is passing through this XOR network, and this XOR network is generating actual pattern that will be fed to different scan chains. So, after the scan chains have been filled, then it will be applied, the circuit will operate in the normal mode, and the response will be captured, and they actually, when these successive patterns are coming, so the responses are getting added up in this MISR, this multiple input signature register, and then when all the inputs when this and it is serially taken out. So, from the tester, the serially the test data is coming in and the compacted response is going out. So, this type of the situation gives rise to this linear decompression schemes. A typical example may be like this, maybe we have got 3 bits coming from ATE S1, S2 and S3, and then we have got this decompressor made up of 3 XOR gates, and some of the lines are direct, like O1, then this O4. So, these lines are directly taken from say S2, S3 etc., and rest of the lines are generated by a combination of these. So, this is done actually by means of that decompression that Gaussian elimination process to get a particular test pattern, what should be the seed value. So, that is obtained, and then that seed value is fed from the ATE, and this decompressor is actually calculating this response pattern that will be fed to the circuit for testing. So, there can be fixed length sequential linear decompressor. So, here from the tester we get B channels, from the B channels that feed this LFSR. This LFSR generates some pattern, and that pattern passes through a combinational linear expander. So, and then this linear expander, so this is giving us n number of bits. So, each of these scan chains are m bit wide. So, in different cycles this LFSR will generate patterns, and those patterns will be fed bit by bit into this scan chain slice. So, in the first clock cycle, the first slice will be loaded, then the next slice will be loaded. So, that way these scan chains are getting loaded. So, you see this LFSR is a B bit LFSR, because this parallel load sort of facility may be there, and then this combinational linear expander. So, this is this will be doing this expansion process, and then it will be put into this circuit. So, maybe from tester we get a single pattern, and then it goes on doing the thing. So, that can also be done. We can also have variable length sequential linear decompressor. So, here it can vary the number of free variables. So, basically what is happening is that we have got B channels from the tester. Now, there is a B to N combinational linear expander. So, after that this so these n bits are coming. So, out of these n bits, so this out of this n bits, so it is divided into B number of channels. So, each of them is having n by B number of bits, and they are actually fed into this LFSR. So, this LFSR, so it is 1 bit will be 1 bit will be taken from the LFSR, and then it is further feeding n by b into m minus 1 bit LFSR. So, remaining m minus 1 bits will be taken from this LFSR, and the 1 bit will be taken from this. So, that way different scan chains will be fed by doing this transfer. So, encoding efficiency is better because the structure itself is quite complex, and we can have more control logic and control information that will be required, like how are we going to do the expansion, then controlling this LFSR to generate the bits, and these extended LFSRs to generate the extended pattern. So, that way the control becomes a bit complex. There are combinations like linear and non-linear decompressions. So, linear decompression is that XOR network, this XOR network based strategy, or maybe we can augment it with an LFSR. and after that we have got this nonlinear decompressor. So, nonlinear decompression are actually the dictionary based approaches that we have seen. Now, if we combine these two together, then it can give rise to further compression. Okay. So, the reason behind this is like this: the specified bits tend to be highly correlated. The reason is that if the first test pattern has excited some faults and the second test pattern excites some fault in the which is close to it, then it is very much likely that due to this physical proximity of two faults, the many of the bits of the test patterns will be same. So, this the specified bits of the test patterns, they are going to be same. So, so if we are doing a linear decompression, then they so that may give rise to the if we take say difference of two successive patterns and all that. So, that will give rise to 0, large number of zeros. So, after this linear decompressing has been done, so if we do a non-linear decompressing, so maybe by run length coding or maybe dictionary based coding, so like that. So, there is a chance that we will be achieving further compression. Okay. So, this combined linear and non-linear decompression together, it can achieve greater compression than either of them. Okay. So, that way it is going to be helpful. Next, we look into test stimulus compression. In that category, we will be looking into broadcast scan based scheme. So, broadcast scan based scheme means that there are multiple scan chains, and these multiple scan chains are fed simultaneously in a broadcast mode, and there are several such scan mechanisms. So, we will look into some of them. So, this is the basic idea of broadcast scan chain. So, suppose we have got 3 different circuits, C1, C2 and C3. Now, this C1, C2 and C3, they have their corresponding scan chains SC1, SC2 and up to say SC3. So, if there are k number of circuits, we have got SCK. Now, if the same scan input drives all of them, okay, then the same pattern will be getting loaded into all these scan chains. Now, it may so happen that the one test pattern which is good for C1, it can detect some faults in C1, it can also detect some fault in C2, it can also detect some fault in CK. So, the same pattern may be broadcasted to all the scan chains. So, that is the basic idea of broadcast scan, that is same pattern is loaded into the scan chains of all the circuits. So, so in general the circuits may be different, but in reality what will happen is that I have got only one circuit which may be partitioned and all that. Now, how can we do this thing? How can we tell the ATPG to generate patterns which are same for both the circuits? So, what is done here is that this ATPG for the circuit that we give to ATPG is a bit modified one. What? Like this C1 and C2, these are two circuits. So, if you give ATPG separately the circuits C1 and C2, so it will be generating patterns specific for C1 and specific for C2. So, it is very much possible that the patterns are not similar. However, if we modify the circuit like these two inputs are sorted, so whatever you give here will also appear here, so whatever you give here will also appear here. So, like that. So, if we do this thing, then we can say that if this modified circuit is fed to the ATPG, then it will generate patterns where these bits the bit number 1 of C1 and bit number 1 of C2, they are going to be same. And so, that way if we modify the circuit and give it to the ATPG, so it can generate test patterns which are similar for C1 and C2. Now, in some cases some ATPG tools, they allow you to do this operation. So, it is so even if you do not have two different circuits, so you can constrain the ATPG to tell that certain primary inputs will get the same values. So, that also serves our purpose. Okay. So, if we know that okay, these are the various scan chains in my circuit, and if I want that scan chain 1 and scan chain 2, they should get always get the same value, then we can tell the ATPG that these primary inputs, they should always have the same values. So, instead of constructing another copy of the circuit as it is shown in the diagram, so you can do it by telling the ATPG that these two bits must be same and things like that. So, it can also be used for a pipeline circuit. Like in a pipeline circuit, what happens is that we have got these pipeline stages, the C1, C2, C3. So, there are pipeline stages, and in between the pipeline stages we have got registers which hold the values inputs and outputs of the pipeline stages. So, this SC1, so this is consisting of the register, this is actually the register which feeds values to C1. Similarly, outputs of C1 is stored in SC2, this register SC2, and that way it goes. Okay. Now, for the scan mode of operation, so these registers, so they are converted into scan register by converting the normal flip flops into scan flip flops. Now, again the same thing, now I have got multiple circuits. Okay. Now, it may so happen that for C1, C2, C3 the test patterns are quite similar to each other. So, in that case we can give the same scan input to all of them. So, this scan input is coming to SC1, SC2, SC3 and all of them. So, it is that again that ATPG tool, it can be instructed that this the first cell of SC1, SC2, SC3 they should get the same value. Now, the point is that in this way it will be detecting many of the faults, but the response compaction becomes another issue. So, for the response compaction part, so we can have one multiple input signature register. So, it is basically it will be compacting all these responses into one signature, and it will be calculated here, and that will be serially outputted from the circuit. So, this way for pipeline circuit also we can use a broadcast scan based approach. There is another architecture which is known as Illinois scan architecture. So, this has got the name because the people, they were from the University of Illinois. So, there we have, so what happens is that some of the faults that can be detected by having similar content in all the scan chains, whereas some other faults, so they will require some exclusive patterns where the scan chains are to be loaded in a different way. Okay. So, what is done is that, say this scan chain segments, segment 1, 2, 3, 4. So, they may constitute 4 multiple scan chains, 4 parallel scan chains. So, what is done, the same scanning input is going to all of them. Okay. So, in the broadcast mode, the same scanning input scan input will go to all the segments. So, they will get the same pattern. So, that way the testing will be fast because the loading time will be less. Now, after that there will certain faults will remain which will not be tested by this broadcast scan based method. So, then all these scan chains, they will be joined together or stitched together into a serial scan chain, and then in the serial mode the scanning comes to the segment 1, output of segment 1 is connected to input of segment 2, like that. So, this constitutes a serial scan chain. So, the whatever scanning pattern is coming, so that will fill up this scan chain, and then then that pattern will be applied. So, for hard faults, so we need to go to the serial chain mode, and the patterns are to be applied in the serial chain chain mode. Sometimes we can reconfigure this broadcast scan. So, reduce the number of channels that are required. So, we can reconfigure the broadcast scan architecture, like this segment 1 was connected to segment 2. So, maybe we can do it in a different way. So, there can be 2 possible strategies. One is static reconfiguration, one is dynamic reconfiguration. In static reconfiguration, so when a new pattern is applied, so we can change the structure. So, we can change the configuration of the scan chains. On the other hand, in dynamic configuration, so it will, while the pattern is being scanned in, so then also the configuration may change. So, this is a typical example. Like you see, if you look into this particular structure, you see that, so for suppose a scan chain 1 will get this particular pattern, scan chain 2 is supposed to get this pattern. So, this is the thing. Now, you see that if you look into this scan chain 1 and scan chain 2, they are compatible to each other. Like if so, scan chain 1 this column 1. So, this column 1 and column 2. So, they are compatible to each other. So, this is 1 and this is x, and this is x, this, so they are all similar, like this is x and this is 0. So, I can put a 0 here. So, that way these columns 1 and 2 they are compatible. In fact, this 2, 3 and 6. So, this 2, 3, 2, 3. So, they are compatible. Similarly, 2, 3 and 6. So, this one also. So, these 3 are 2, 3 and 6. So, these are all compatible. Okay. So, that way I can do this thing, that is I can combine them into one particular sequence. So, I can combine them into the this 2, 3, 6. This is scan chain 2, 3 and 6. So, this scan chain 2, 3 and 6. So, they are compatible, like this is x, x 0, x 1. I am sorry. So, for the previous explanation by column. So, this is actually by the scan chain. So, 2, 3 scan chain 2, scan chain 3 and scan chain 6. So, they are compatible to each other. Then scan chain 7, scan chain 7 is not compatible to anybody. So, that way this is this may be it is taken separately. So, it is compatible with scan chain 2, but 2 is already grouped with it is already grouped. So, with 2, 3, 6. So, I cannot group it together with 2 again. So, 3 then 5 and 8. So, 5 and 8. So, they are compatible. So, 5 and 8, scan chain 5 and scan chain 8 are compatible. So, that way it seems that I can whenever I am broadcasting pattern. So, I can broadcast the same pattern to scan chains 2, 3 and 6. I can broadcast the same pattern to scan chains 5 and 8 and again to scan chains 1 and 4. So, I can have this type of configuration where this scan chain 2, 3, 6 they are getting the same pattern. So, this is 2, this is 3 and this is 6, they are getting the same pattern, same scan input will be coming there. Then this scan chain 7 is having one scan input, then this 5 and 8. So, they are having another scan input. Okay. And then this 1 and 4 they will be having another input. Okay. So, ultimately if I have got these 3, I need these 3 separate inputs to come, and then in the broadcast scan mode this these few test patterns. So, this is the first test pattern. So, these test patterns can be loaded. Okay. So, after that what happens is that after this part has been done, for the second part we can see that 1 and 6. So, they are compatible. So, this is x, this is 0. So, this is 0 0 either x or 0. So, that way 1 and 6 are compatible, then 2 and 4 are compatible. So, 2 and 4. So, they are compatible. So, this way we can see that after we have shifted these many bits, this 5 bits. So, it is possible that it is required that a different type of configuration will exist. Okay. So, at that time I need to change the configuration. So, for the second part I need to change the configuration. So, if the scan chain this scan chain connection can be reconfigured, then it can help us in the shifting process. So, from the control line, so it can select this scan chain 1. So, when in the first if in the first session I can say that this scan chain 1 is getting the value from 4 and scan chain 1 is getting the value 4. So, if you see here scan chain 1 should get the input from pin 4. Okay. Then in the second part, so scan chain 1 should get the input from pin 1. So, in the second part you see the scan chain 1 should get input from the pin 1. So, similarly, scan chain 4 in part the first part it should get from pin 4, in the second part it should get input from pin 2. So, you see that 4 in the first one it should get from input 4, the second one it should get from pin 2. So, this way this network can be configured, this network can be designed, and by through this control line. So, we can have this decompressor realized. So, this is from we are getting only 4-bit input, but they are feeding 8 different scan chains. Sometimes we have got another type of structure which is known as virtual scan. So, virtual scan, what happens is that instead of only multiplexers, XOR networks can also be allowed, and in fact we can also allow any other gate networks, AND or NAND, that type of gates can also be possible. So, now the advantage is that since we are allowing other logic, so it is no more linear. So, we do not need to solve linear equations, but we can try to configure those decompressor using those extra gates, so that it gives us a good amount of compression. Then dynamic compaction, it can be effectively utilized during the ATPG process, because dynamic compaction, so it tells that okay, after sending a pattern up to this much, so rest of the remaining part of the pattern, so these two bits are same. So, if this information is available, then the ATPG then the ATPG can generate pattern like that, so that those two bits are same for the remaining part. So, this dynamic compaction, so this will result in very little or no fault coverage loss, because the ATPG itself is doing the manipulation of those bits. Next, we go to the response compaction part. So, so far we have talked about the stimulus compaction, that is the test pattern that we are going to apply. So, that will be applied to the coded pattern will come from the ATE, and it is decompressed by the decoder present at the beginning of the in the circuit, and then it is going to do the stimulus, then it is going to decode the stimulus and apply the stimulus to the circuit. Then the response that is obtained, so again it has to be compacted. So, this response compaction can be done in 3 different modes, like we can have space compaction, we can have time compaction, or we can have some mixed mode of compaction. So, space compaction, because out of say if a circuit has got 100 bits as output, then there is no point keeping all the 100 responses in the as in the signature part. So, we need to store only a few of them. So, that maybe we can do some reduction. So, that is the space compaction. Then we can have time compaction. So, time compaction is maybe I am applying 10,000 patterns. Now, we do not want to remember all the 10,000 responses. So, that way we want to remember some summary of the whole session. So, that way the time compaction can be done, and there can be naturally a mix of these two. So, we will continue in the next class.